Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science. And in this video, we're going to do an example of pumping liquid out of a tank. So here we have a tank, it's full of water, and we want to find the work required to pump all of the water out of the outlet. So here's the outlet 2 meters above the top of the tank, and the tank is 3 meters tall, 8 meters long, and 3 meters wide. Okay. So what we're going to do here is we're going to examine the work required to pump out one tiny little sliver of water, and then we're going to use calculus to basically integrate over all of the little slivers in the tank and find the work required to pump out all of the water. Alright, so in order to do this, what we have to do is imagine we're looking at this from the side, so we're looking at it directly from this side right here. What are we going to see? Well, because this is a triangle, this is a triangular prism type trough here. What we're just going to see if we look at it from this side is just a plain old triangle. So let's go ahead and draw ourselves a little triangle. And here's the side of the trough, and then here's our little spout, our little outlet up there. So now we need to set up a coordinate system. So let me actually move that down ever so slightly. So our little triangle is going to be over here, and we have to put our spout up here. And then we're going to set up a coordinate system. So our coordinate system is going to go from here to here. And what I want to do is put 0 on the bottom. So if 0 is down here, then that means this is 3, because 3 meters tall, that's our tank, 3 meters tall. And then 2 meters above that is our spout, is at the top of the spout, so this has to be 5. Now we could have put 0 here, and then this would be 2, and that would be 5, that'd be totally fine. But I feel like that would complicate a piece of the problem later on. And we could have put 0 here if we wanted to, but I feel like that would complicate a lot of things. So technically you can put 0 wherever you want, but for this particular problem, I feel it's best down here. Alright, now anyway, now let's go ahead and examine one little tiny sliver. So what we're going to do is look at a little tiny sliver right about here. And our sliver, I'm going to say it's at position X. Okay, so the height of the sliver is X. Alright, so we're going to look at a little tiny sliver at height X and thickness delta X. Alright, so remember in calculus, delta X usually represents a really infinitesimal quantity, and what that means is it's a really super teeny tiny quantity. So we have a little sliver of water with a really super teeny tiny thickness that we're calling delta X. And that's going to come into play soon. So what's the work required to pump out just this one little sliver? So we want to take this little tiny sliver and pump it out of the tank through the spout up here. What's the work required to do that? Well, so that's just one little teeny tiny sliver, so we don't need calculus yet, but the work required for that, remember work in general, so let me say work for sliver. Work for the sliver is force multiplied by distance. Okay, and that's going to be, now force is mass times acceleration. So force is mass times acceleration. And what's the distance? Well, the distance is the distance that the sliver has to move to get out of the tank. Now, the top of the tank is here at 3, but in order to get out of the tank, remember the sliver has to be pumped through the top of the spout here. So the sliver basically has to move all the way up to the top of the spout. And what's that distance? Well, basically we're asking what's the distance between 5 and x, and it's just going to be 5 minus x. So this is the distance that the sliver has to move to get out of the tank. So then we can replace distance with 5 minus x because now we know what that is. And it's going to be measured in meters. Alright? Now mass is density times volume. Now, what's the acceleration? Well, the acceleration is going to be the acceleration due to gravity, and the reason is, since we're pumping the little sliver vertically, it's directly vertically out of the tank, this little sliver is going to have to fight the force of gravity on its way out. And the acceleration due to gravity is, for our purposes, approximately 9.8 meters per second squared. Now, I do want to point out something. You might be wondering, well, hey, 0 is here, 3 and 5 are up here, so that means the positive direction is this way, and if gravity is pulling us down in the negative direction, gravity pulls us down in the negative direction, shouldn't the acceleration actually be negative 9.8 meters per second squared? And yes, technically that's true, but the negative sign that would be on this actually cancels out with the negative sign that would be on something else. But what I'm doing is sweeping these details under the rug, kind of pushing that behind the scenes. And it's okay to do that because it's always going to work out that way if we set up a coordinate system like this and do everything else properly. And it's better just to sweep those under the rug and forget about them rather than overcomplicate everything with extra details that are always going to cancel anyway. So I did just want to point that out for the physics buffs who are looking at that thinking, hey, negative direction should be negative. But yes, it is technically, but it's going to cancel with something else soon anyway. So moving on from that. So this is our acceleration, and we still have our distance, 5 minus x meters. All right, now what's the density? So the density, it'll probably be, it depends on your instructor, I guess, but it could be given to you in the problem. Since we're dealing with units of meters here, our density is going to be 1,000 kilograms per meter cubed. All right, now we need to find the volume. So we have everything but the volume. How do we get the volume? Now what we need, let's go back over here to this picture, and let's put our sliver on this picture. So we have our sliver here. Okay, here's our little sliver. Now the volume of the sliver is going to be, basically the sliver here, if I had better artistic skills, we would see that the sliver is essentially just a rectangle, right? Well, it's not really a rectangle, it's three-dimensional. It's a three-dimensional object. It has thickness delta x. So the thickness is the length in this direction. Okay, so that's the thickness, and it's delta x. Now, as we can see, our little sliver of water here stretches across the entire tank, and the entire tank is 8 meters long. So the length of the sliver in this direction is 8 meters, okay? So far we have that the volume is delta x times 8 times what? Well, we have this direction, we have this direction, now we just need this direction. So what's the length in that direction? Well, here, let's go back to this picture here. I'm going to call that W, okay? And we're going to use properties of similar triangles to figure out what W is in terms of x. Why do we need W in terms of x? Because eventually we want to push everything into an integral, and we're going to integrate with respect to x. So we have to be able to express this in terms of x. Okay, so this is W. Now remember, this is the top of the tank right here, so this whole thing is 3. Okay, and the height of the entire triangle is 3 because here's 0, here's 3, right? And because the tank is 3 meters tall. So what we can do is use similar triangles. What are the similar triangles? Well, here's our small triangle sitting inside of the larger triangle. So properties of similar triangles tell us that what we have is the height of the smaller triangle, which is just x, right? The smaller triangle has height x, because here's 0, here's x. So the height of the small triangle is x, divided by the height of the large triangle, which is 3, equals the width of the small triangle, which is w, divided by the width of the large triangle, which is 3. So now we can use this to express w in terms of x. Let's multiply both sides by 3, and we end up with x equals w, or in other words, w equals x. So that's really great, actually. That really simplifies things for us, because now this w just equals x. So what that means is that the length of our little tiny sliver in this direction is just x. So the volume of our sliver is delta x times 8 times x. Okay? So going back to here, density is 1,000 kilograms per meter cubed. Volume is, let's say, 8x delta x meters cubed. And then we're still multiplying by 9.8 meters per second squared, and then multiplying by 5 minus x meters. All right, now we just want to verify that the units actually work out. So meters cubed cancels with this meters cubed over here. And then we have kilogram meters per second squared, and then meters again. And those are the correct units. So everything is great. Now we just have to simplify this a little bit. So we have 1,000 times 8 times 9.8. That's going to be 78,400. and then we have an x, and then 5 minus x, and then we have our delta x. Okay, so there's a reason that I rearrange everything like this. So this is the work required to pump out just this one tiny sliver. Okay, that's the work for just the one tiny sliver. So let's go ahead and go to the next page and summarize that. So the work for one sliver is 78,400 times x times 5 minus x times delta x. All right? Okay, so what's the work for all of the slivers? Well, for all of the slivers, what we want to do is, let's express that as W. So W is going to represent the work required to pump out all of the water. Now, to get all of the water, that's basically getting all of the little tiny slivers, which essentially amounts to integrating. So now we want to integrate this expression here. Okay, we're going to integrate that entire thing. So we integrate over all of the slivers, 78,400x is 5 minus x, and then dx. Remember, when you push delta x into the limit process, in other words, when you put delta x into an integral, it becomes dx. So don't forget about that. Now, what are the limits of integration? Well, spoiler alert, one of them is 0. So what we want to do, we always want to integrate where the liquid is, okay? Because remember, we're integrating over all of the slivers, so we have to integrate where the slivers are. In other words, integrate where all the liquid is. And here, our liquid goes from 0 to 3 because the tank is full, so the liquid is in the entire tank is full of liquid, so our liquid goes from 0 to 3. So our limits of integration are going to be from 0 to 3. Okay, and this is the integral that gives us the work required to pump all of the water out of the tank. So let's go ahead and evaluate this. So we can pull out the 78,400, and then we're going to integrate from 0 to 3. Let's distribute the x. So we're going to get 5x minus x squared. That's a squared. Let's make that a little better. Dx. And then we have 78,400 times, when we integrate, we're going to get 5 halves x squared minus 1/3 x cubed, evaluated from 0 to 3. So now we just multiply 78,400 times, let's evaluate this at the top, we get 5 halves times 9 minus 1/3 times 27. And then we have to subtract and evaluate at the bottom, but notice at the bottom x is 0, so all of this is just 0 at the bottom. And that's great, that's really nice, and that's actually why I set up my coordinate system like this. If we put 0 up here, we would end up integrating from 2 to 5 instead of 0 to 3, because this would be 2, this would be 5, our liquid would be between 2 and 5. So personally, I feel like that would make the integral more complicated, even though it would make the 5 minus x would be something simpler, but the limits of integration, I feel like they'd be more complicated. So anyway, let's just simplify this then. So we have 78,400 times, this is 45 over 2, minus, so 1/3 times 27 is 9, and 9 times 2 over 2 is 18 over 2. So this is 45 over 2 minus 18 over 2. And then that's going to be 78,400 multiplied by 45 minus 18 is 27. 27 over 2. And then 78,400 times 27 over 2, that's going to give us, these numbers are getting a little big now, so let's bust out the calculator. And we're going to have 78,400 times 27 divided by 2 is 1,058,400. So we have 1,058,400, and joules is the unit of work there. So basically what we just found out is that it takes 1,058,400 joules of work to pump all of the liquid out of this tank here. Okay. So this has been an example of pumping liquid out of a tank, and I hope you found this video helpful, and thank you for watching.